All right, I'm going to talk about now what makes Power PMAC. This is the meat and bones of Power PMAC right here. Power PMAC data structures. For those of you who are familiar with our previous, our last generation of motion controller, memory locations in Turbo PMAC had a memory map, so to speak, that had things like position registers and velocity registers. But in Power PMAC, we did something a lot more useful that will not only make it easier for you to remember what a particular element is in Power PMAC, but it will also make your programming self-documenting, because it will be a descriptive name for these items. And this is what Power PMAC data structures are. So this is the main provided method of organizing Power PMAC information. So both hardware and software memory registers. And when I say a hardware register, I mean, for example, we have these Axis interface cards. There's an ASIC in here, and there's a number of registers on that ASIC. So that's it's an actual hardware register. Whereas in the Power PMAC CPU, there's memory, volatile and non-volatile memory. Those are pure memory registers. But as far as Power PMAC is concerned, like it was with Turbo PMAC, everything is memory mapped into its memory, into its addressable memory. So this includes what we call saved setup elements, sort of like the old I variables in Turbo PMAC. Unsaved control elements, things that might change the behavior of Power PMAC, but it's never saved in that state. On a power cycle, it returns back to its normal initialized state, and we'll talk about some of those in detail. And then there's some status elements that are read-only, so you would never write to them because they provide some status information. Let's say the current motor velocity is not something you would ever write to because it's telling you what the motor velocity is, or the motor position register. It's a status element. It's not something you would really ever write to, although there are some status elements that you can write to, and that does make sense. We'll talk about those as we go through the various elements here in class. So this mostly replaces the I and M variable usage of the regular PMAC and Turbo PMAC. All of these Power PMAC data structures, they are predefined by us. So you cannot create your own data structures, at least in the script environment. Of course, you could create your own structures in the C environment, but you wouldn't have access to them in the script environment. So these are things that we've created that you can use in both the C and script. So all of these structures that we have, you can use in both C and script. You never need to know the numerical address of any structure element now. As in Turbo PMAC, it was important to know what the address was of a memory register so you could make an M variable definition. Now in Power PMAC, you never really need to know the address because you'll always use the structure element itself. And in a couple of seconds here, we'll see a few structure elements. And then most of you guys are from back east, right? So maybe we'll go ahead and break for lunch here shortly. That way everybody doesn't feel too hungry for too long. The Power PMAC data structures, they're accessible through online commands, both in script and C programs. And the IDE, remember I talked about this in IntelliSense. So as you're typing in these structure names in the IDE, so I'm going to start typing in a structure name that I'm aware of, MOT, so motor. Notice it brings up the entire word motor. I can hit the enter key to put in that. I can fill it in with an index, and then I start getting ready to type in more of the structure name. It brings up all of the possibilities that could be here. I'll just go ahead and pick the first one. And then when I hit enter again, it is asking for the value of that structure element. So the IntelliSense can be very useful to you as you're doing your programming. It not only works in that terminal window, it also works in the editor screen. So it can many times help you complete the text of your motion programs, your PLCs. If you click on F1, it will bring you to the manual as help in the IDE. So if I go back and then I do F1, it brings up the manual as help, telling me, oh, what is motor sub x dot abort TA? It gives me a complete description, range, units, default values. And what do you know? The value that I have in mind just happens to be the default, which would be expected. I'm sorry? Can you do that again? Sure. So let's go back to the IDE. So let's say I typed in anything. Let's say instead of picking that one, I picked motor dot. Let's pick abs phase pause SF, absolute position scale factor. And then I'll hit the F1 key. And then it'll bring me up to a description of what that is. All right, so we started talking about data structures, the generic concept for Power PMAC called data structures. These are all of the registers, so to speak, memory registers of Power PMAC. So in the script environment, you access these data structures with both online commands and buffered program commands. Remember, Power PMAC is a computer, and the majority of what goes on in any Power PMAC application are online commands being sent to Power PMAC. There are certain online commands that when you send them to Power PMAC, it tells Power PMAC, oh, I want to create a buffer now, so all the remaining commands that are sent to me will now go into a buffer. And then there's a special command that will close that buffer, and then from that point on, all online commands are just immediately executed commands. Like, for example, we're going to ask for the value of motor 1's absolute phase position scale factor, and it's currently a value of 0. Or we're going to ask Power PMAC for the version of firmware. And this one is 2.001. Or we're going to ask Power PMAC for what CPU type it has. These are all online commands, and Power PMAC gives an immediate response. Now I could give it a special command. I could say open program 1, and now Power PMAC has been put into a special mode with that online command, telling it, oh, the rest of the stuff I send you now is considered, will be buffered commands placed into this buffer called prog1, program 1. And then the close command will then tell Power PMAC, oh, I'm done. Now we're back to online commands. I can go back to entering online commands. So that's what I mean by the difference between online and buffered commands. And so you don't need to really do anything with the detail of this because the IDE is going to automatically take care of that for you. When you create your script programs, your buffered motion programs and PLCs in the IDE, it takes care of all those lower level details for you. In the script environment access, structure and element names are not case sensitive. So everything can be all uppercase, could be all lowercase, you could mix upper and lowercase. Power PMAC really doesn't care. In the C, on the other hand, C is always case sensitive. Any of you who are C programmers, you're probably very well aware of case sensitivity and how you can really screw things up by having similar macro names or function names where there's just a slight difference in case and all of a sudden weird stuff happens. But in the script environment, there are no problems like that in Power PMAC, in the script environment. So there's no need to include any header files for script access. Everything is built in. Everything is recognized automatically. There's no need to declare any of these predefined elements that we give you. Script environment automatically also performs all type matching of different variable types, integers to floating point. Power PMAC prevents user changes to write protected elements. So there are some elements that will be considered write protected. I'll talk about that a little bit later on, the details. So there's an error returned for an online command attempt to access a write protected structure. If it happens in a buffered program, let's say the buffered program doesn't properly clear the write protection, basically there is no reported error, but there's a no operation that goes on in that buffered program. So it's as if that command did not exist. Now, many times there are bits of status elements that can tell you if something like this has occurred. We'll talk about that when we get, we'll talk about those particular occurrences as we find them throughout this class. Power PMAC also prevents out-of-range values from being assigned. So there is an error that's returned for an out-of-range. If this happens inside of a buffered program, it basically just skips it. There's a no op. No error is reported, so the program won't abort. It just won't do anything. So if you try to assign the wrong type of numeric to a structure element that maybe it's not looking for a numeric, then it will produce an out-of-range value. Or you try to put too big of a number in a structure element that requires a smaller number, like it's only it's only looking for a small binary value or a small an 8-bit value. The motion programmer, the PLC, will not generate an error. It'll just skip that, and no values will change inside that structure element. So there's classes of these structure elements, and we're going to touch on that right now. And then we'll very shortly get into some specific structure elements. So there are saved setup elements. These are the ones that when you type a save command, they're saved into Flash. They all will have a factory default value that gets reset on initialization, $$, $****. That clears everything back to factory defaults. And so all of the factory default values, remember when we had the help up earlier, we saw that there's a default value. When we talk about the factory default value, you'll find that in the software reference manual under the listing for each of these structure elements, also in the help. The last saved values are copied from Flash memory on a normal power up or reset. And I'll mention why I may have used this word normal power up or reset, because there are some special activities that happen on an abnormal power up and reset, and we'll talk about what that means a little bit later. And the present active values are copied into Flash memory on a save command. So remember, you're changing a structure element in Power PMAC, it's on the volatile side of memory. Until you type a save command, that value that's saved on the volatile side of memory is now saved into the Flash. Nothing is really ever used in the Flash while you're running your Power PMAC. Everything is always used on the volatile side, but when you type a save command, it's like writing to your hard drive in your PC. It's putting a copy of that in a permanent location in the Flash side. There's also what we call non-saved control elements, and these usually have a default value. Almost always there's 0. And on power up and reset, every time you power up your PMAC or you do a reset, $$, they'll be set back to these default values. And you can change them any time in the application. That's the typical usage of these non-saved control elements, and they're not affected by the save command because they're not saved. Then there are what we call status elements. These values are automatically set by the Power PMAC because the Power PMAC is trying to say something like a status word. If there's an error bit, a servo error is a bit in Power PMAC. That's a status element. You can't really write to it. Power PMAC is going to always be writing to it with the current state of the status of servo. And most of them are write protected in the script environment, so you couldn't write to them anyway. Some you can write under special considerations. There are special operations that allow you to write. For example, the position register in one of the ASICs, the actual encoder counter value, normally you wouldn't write to it, but there are ways that you can, by telling Power PMAC, okay, set this bit, now let me write to the encoder counter. I can now put my own value in the encoder counter. That's not a normal thing you would do, and some of the ASICs you can't do it at all. On some of the older ones you can. There are some special techniques that this can be done. And each class of these elements, as we saw previously, they have their own chapter in the Power PMAC software reference manual. So some important data structures. Now we get into the actual details here. So there is a top-level structure name, and then there are sub-level structure names, and then there are even sub-sub-level structure names. Just like in a C structure, you have a top-level structure, dot, the element name, dot, the sub-name. So that is the same technique that's used in Power PMAC. So some of these upper-level structures that we have, sys, these are global system elements. They usually affect the entire setup of the card. Some of these are saved setup elements. Some of them are status setup elements. Some of them there are some control elements. But this is just the upper level name of these data structures. Motor bracket X. So this is the motor elements indexed by motor number. So all indices in Power PMAC start at 0 and go to whatever the maximum index for that feature in Power PMAC has. As in motors, you can go up to 256 motors, so you get 0 to 255. The default settings in Power PMAC, or at least that the IDE sets up for you, are 32 motors. The firmware automatically sets itself up for 128 motors, but you can increase that by changing other structure elements to give you more available motors if you so desire. Some of the elements that have another sub-element, motor sub X dot servo dot motor, whatever that happens to be. So these are the motor servo control elements that belong to the servo algorithm. Chord sub X, enc table sub X, comp table, gate 1, and then gate 1 dot. There's upper level names that are global to the entire servo gate. This is the DSP gate 1. And then there's gate 1 sub I dot chan sub J. So these are the per channel elements. For example, an encoder decode for a particular channel on the gate array, or the PFM output for a particular channel on the gate array. The DSP gate 2 also has the same data structures. Gate 2 sub I, gate 2 sub I dot chan sub J. Gate 3, same thing. This is the DSP gate 3. Now, DSP gate 3 was designed for Power PMAC only. The gate 1 and the gate 2s are also used with Turbo PMAC. And so Power PMAC can work with the Turbo PMAC gate 1 and gate 2 ASIC servo ICs. Gate I/O, we have our own, Delta Tau has our own I/O gate, so we call that gate I/O sub I, and it has a number of elements that belong to it. Gather dot and macro dot, so these are all the data structures for gathering, all of the gather elements, all the features of gathering, and then all of the features of macro ring elements. Specifying the data structure indices. Index is in square brackets, not parentheses, and the index has to be an integer constant or a local L variable. Cannot be just any generic variable. So the only two ways you can specify the index is either through a numeric literal constant or a local L variable. So no expressions, no fractional values. If you're calculating an index value, you would do this in a separate program line and then assign it to an L variable, just like we have up here. L0 equals LData.motor, and then motor bracket L0 dot jog speed. And then we set it to a value. Indices always start at 0. So Power PMAC, all indices start at 0. The motor sub X index value matches the motor number. So in Power PMAC, there is a motor 0. In Power PMAC, there is a coordinate system 0. Most people won't ever use motor 0 or coordinate system 0 for anything specific. It will probably be saved for special motor functions, maybe a special phantom or master motor. Same thing with the coordinate system. Most standard typical use of our automatic setup programs, we'll start with motor 1 and we'll start with coordinate system 1. And I would recommend keeping it that way so that if you ever had someone else come in from the, you hire somebody else who is familiar with Power PMAC and they're going to be working on your system, if you do things in the standard way that we suggest, they'll hopefully be trained in that standard way and things will be a lot easier. Having said that, Power PMAC does have just a wealth of features so that there are many things that you can do with Power PMAC. The ASIC index value matches the ASIC number, but the ASIC numbering scheme is different from that in Turbo PMAC, and we'll see this as we go along. The gate 1 and the gate 2, the indexes that come after gate 1 and gate 2 aren't the kind of indexes you would see on the gate 3 and the IO gate. Gate 3 and IO gate always go 0, 1, 2, 3, 4, so on and so forth, whereas gate 1 and gate 2 are just a little bit different. Gate 2, for the most part, will follow that numbering scheme, but definitely gate 1 will not. And we'll see that a little bit later on. The ASIC channel index, so when we have the gate 1 sub I dot chan sub j, so the j is the ASIC channel value, and that goes from, of course, remember, all indices in Power PMAC start at 0 and go to 3. So channels 1, 2, 3, and 4 are indices 0, 1, 2, and 3. That's all we're trying to say here. And constant index values range from 0 to sys max items minus 1. So this is the item that gives you the max, that is the structure name that tells you what are the maximum number of indices that I can use on any particular PMAC structure name. Now, we talked about how you never need to know the actual numerical address of any PMAC register, any PMAC memory location, and that is because to specify the address of an element, you put the .a suffix at the end of the element. That tells you that now that value represents the address of that element, because in many cases, some of the structure elements in Power PMAC are pointers to something. And so you may need to tell another structure element the address of another structure element. So generally, you do not need to actually know the numerical value of the address. And in one case, if you did actually use the hard-coded value of the address, depending on how much you had installed in your Power PMAC and where it happened to be, the address might actually be different from one system to the next. So using this built-in scheme for addressing, getting the address of a structure element is by far the best way to do this, because it always guarantees it gets the correct address that might be different from one implementation to the next. And if you do happen to need the address, you can always get it through a numerical value by doing the query elementName.a, and then it will tell you, for example, if I go back to here, and let's see, what was a structure that I had been previously looking at? The up arrow key, by the way, is going to cycle me through all of my last commands. And so, I don't know, what's the address of this particular structure element? It's somewhere in memory. And so there's the address, $BE287A68. Power PMAC is going to always report the addresses in hexadecimal. And this is a monolithic address from Power PMAC memory, starting at address value of 0 all the way to the highest address Power PMAC can have. But rarely would you ever need to know the actual address of a Power PMAC. The P at the beginning of an element name, and when we talk about element name versus complete structure, the complete structure name is the upper structure level and then its element name. So we have motor dot, in the case of the last one that we just did, motor.abs phase pos SF. So the entire structure element is called motor sub 1.abs phase pos SF for the absolute position scale factor. The element name by itself is just abs phase pos scale factor. So many times we'll just refer to the element name because we'll have remembered, oh, it's one of the motor structures. And right now I don't care what motor I'm talking about. I'm just talking generics of that particular element. So the P at the beginning of an element name specifies it's a pointer to something. And so when we evaluate something to send to it, we're probably going to use the .a suffix at the end. For example, we have a structure element called PDAC for each motor. And it's going to look at one of the output registers of the servo gate, whatever servo gate it happens to be connected to. So we can see here, it's looking at a gate 1. It's number 4 in its index. It's looking at the first channel and the first PWM channel, and then we say .a to tell it it's the address. So there's no point of us needing to know the address of it. We just need to tell it where motor 1's output PDAC pointer is going to be looking at to send the output of the PID loop. PDAC is the generic motor output for that particular motor's PID loop. If you query it, you just say motor2.pdac, then Power PMAC will respond with the structure element name that it's pointing to. It won't respond with the address. It'll respond with the structure element name. If you were to query that element address, then it will respond with the actual pure hexadecimal value for the address. C access to data structures. So in the C environment, and I won't talk too much about C. We have an entire section a little bit later on this week on utilizing C with Power PMAC. But you have to include the header file that has all of the definitions for these structures. It's in RTGP SHM.H. So that will always be included at the top. And this then allows you access the standard C structure access. The structure name in C is PSHM for pointer to shared memory. And then the data structure element that we saw before. So there's motor data structure elements, there's the coordinate system data structure elements, and we can get a hold of all of those by using PSHM. So for example, we can see here, motor 1 jog speed. So in C, we would say PSHM points to motor 1 jog speed. Keep in mind, in the C, you must use the proper capitalization on the structure names. Otherwise, it won't be recognized because it's not in the C header file. And remember the types, the values, all of that auto typing that's done in the script environment is not done in C. So it's up to you to make sure that you have the right typing done in your C code. We'll talk more about that when we get into the C. Element names, like I said, are case sensitive. There's no write protection or out of range or saturation protection. And there are a few structure elements that you can't access in C because what they end up being is they end up not being true structure element names. They're actually clothed in a function call inside of Power PMAC. So some of them you couldn't even access them through through the C environment. And when those come up, there's very few of those. I'll point them out. For the hardware elements, like the different gates, the different ASICs, anything that's pointing to real, true hardware in C, it's always the full 32-bit that you get. Even if the structure element in the script is only pointing to a section of that 32 bits, for whatever feature it is in Power PMAC, in the C environment, it's always going to look at the entire 32 bits, whether the structure name is pointing at the top 32 or somewhere near the bottom or somewhere near the middle. It's up to you to make sure that you access the right bits in that element name. So you have to do masking and shifting to isolate the partial word element. So the script full word element of the same name may be less than 32 bits. For example, gate1 sub I .pwm control, it's only 24 bits. It's the high 24 bits of the 32 bits, so you need to make sure that if you use it in the C environment, that you isolate those high 24 bits and get rid of the low 8 bits. Otherwise, you could run into a lot of trouble, and you would have weird scaling if you didn't do that. C, access to hardware data structures, so we can share these data structures that aren't part of the pointer to shared memory. And there's a couple of methods. We have the built-in API inside of Power PMAC that allows you to get a pointer to those memory structures. And then you could also create your own definition through access and then isolation of these element structures with shifting bits and then anding out. I won't go into any greater detail. We'll talk about this again when we get into the C section of class.